Hello, uh, welcome back. So in this video, we will solve a few problems so that we get better familiarity with MOS capacitors. So in the last few lectures, we have understood what a MOS CV means and how it looks like, and why, what is the physical reasons why it behaves the way it does, right? So now let us try to solve a couple of problems. Okay. The first problem we would like to solve is this. So we are given a CV curve. Okay. And some, at 2 points, the CV, the capacitance numbers are also given to us. And this capacitor, MOS capacitor, is assumed to be ideal. Okay. It's an ideal MOS capacitor. Okay. So there are a few questions here, and we want to answer them one by one. So first of all, when you look at the CV, is a semiconductor N-type or P-type? How do we answer that? Well, first we have to identify where is the inversion, right? So there is oxide capacitance, accumulation capacitance, and the inversion capacitance. So from our understanding of the concepts, we saw that whenever the oxide is, capacitance is involved, it doesn't change its voltage. So this part is the accumulation region. And then we go towards depletion. And finally, we hit it, at this point, we hit the inversion. So at positive voltages, we are having smaller capacitance. So it looks like it is a P-type substrate, because when you have a P-type substrate, you apply a voltage, then it creates a depletion region, and then you'll have inversion. So it looks like it's a P-type, right? So you need to be able to explain why it is P-type. You can't simply say that, oh, wherever it is, if your capacitance is lower in the positive gate voltages, it is P-type, because I could have as easily a capacitance curve which looks like this. Here also in the positive gate voltages, you're having the smaller capacitance, but this is not P-type substrate. This is an N-type substrate. So the aspect we need to track is, as you increase the voltage, what is happening to the capacitance? Okay. Here, as you increase the voltage, it's increasing. So this is clearly not going to satisfy the P-type sort of behavior. Okay. So that's why we need to be able to clearly explain why, from looking at the transition from accumulation to inversion, we conclude that it is a P-type semiconductor. All right, good. The next question is, draw the energy band diagram corresponding to the point 1. Well, yeah, point 1 is here. So clearly it's an accumulation. So the question is an indirect way of asking you to draw the band diagram for a MOS capacitor in accumulation. Well, how would you draw that? So whenever we want to draw the band diagrams, first draw the bulk. Okay, for especially MOS capacitors, you can draw the bulk first. Right, I'll identify the bulk regions this way. And we concluded that it's a P-type semiconductor. So I will put my EF closer to EV. Right? This is my bands in the bulk. And now we are saying that it's an accumulation. So what are accumulating? So it's a majority carriers are P-type, holes, right? So basically, you're going to have more holes closer to the interface, right? So I need to bend my bands slightly in such a way that I depict on this black. So this is my accumulation of holes. Okay. Because if I extend my Fermi energy till here, so I have the distance between EF and EV reducing. So that means there are more holes. So clearly the bands are bending upwards. So after that, almost without any thought, you could draw that electric field will be in the same direction in the oxide. Okay. We have seen that unless there is some charge, discrete charge somewhere, additional charge sheet, this won't change. Okay, we have seen in the charge block diagrams, right? Block charge diagrams, we have seen block field diagrams. Okay, so this is how it is. And now what happens to the Fermi level in the metal? Well, we are applying a negative voltage and we are reaching accumulation. So EF can't simply be at the same level. This will be wrong. Right? This is without any voltage. So this will be wrong if you draw EF of metal here. We are applying a negative voltage. So if you apply negative voltage, EF is going to shift up. Right? And this difference is going to be Q times Vg, applied voltage. So this is how a band diagram looks like. Of course, always this is not to scale, right? We remember this always. We are only showing the essential physics because this distance is going to be 1.12 eV band gap of silicon, and this we saw was close to 3 eV, right? Or even 4 eV. Electron affinity was close to 4 eV for silicon, and this is close to maybe 3 to 4 eV. So we are not drawing it to scale, okay? But we are showing the essential physics. That's all, okay? One way of representing that, you are not drawing to scale would be to put something like this. This mark indicates that there is a break in the axis there. Okay? All right. So this is how a band diagram will look like in accumulation. You should also practice how the band diagram looks like in inversion. Okay, please do that. It's helpful for you. Okay. Now, the third question is draw the block charge diagram corresponding to the point 2. Well, yeah, point 2 is here. It's clearly in inversion. So how does the block charge look like? To draw the block charge diagram in inversion, what I would need is I'll draw the basic axis. Let's say this is my X, right? And I'll assume that this is my oxide thickness. So this is, I'll put a straight line there. So I'll call this as X equal to, this is X equal to 0. So this thickness, I'll assume that it is Tox. Okay. So now clearly we are having inversion, right? So what does it mean? We are also applying positive voltage. So there should be a positive charge on the gate, and that will be right at the interface. Okay, I can't emphasize this enough. Whenever we draw a thin line like this, it essentially means that it's at the interface. This is my plus Q, right? What is this gate voltage doing? Positive gate voltage is pushing the holes away from the interface. So on the semiconductor side, this was a P-type semiconductor, right? And we push away the holes. What remains is a exposed acceptor ion, right? So that's why I should get, this is my depletion charge. So yeah, depletion charge. How is this formed? This is basically an A minus. So you're pushing away something, okay? And by the way, since it's in inversion, what will be the thickness of the depletion region? This region is going to be W max, right? Maximum depletion width. How much is the maximum depletion width? Well, that is a width when you calculate the width corresponding to surface potential of 2 phi f. Okay, when you do that, you get the maximum depletion width. Okay, is that all? Well, no, we are not at threshold. We are actually much beyond threshold. There should be a substantial number of inversion charges. The inversion charges for a P-type semiconductor are electrons, right? So I need to show my inversion charge here. So I will draw so a structure like this. Basically, this is showing you that these are electrons at the interface. So overall, your plus Q, whatever you have, right? Q plus Q should be equal to Q depletion plus Q inversion. Okay, the sum, okay, in terms of magnitude, they should be equal. Okay, both are negative, so sum it up. That should be the charge balance. Always the charge balance has to be maintained. There is no other escape from that. It's one of the fundamental laws of physics. Okay, fine. So this is done. How about the next part? If the area of the MOS capacitor is 3 into 10 power minus 3 centimeter square, what is the thickness of the oxide? Why are we given area? Okay. So, well, the reason for that is we know what is oxide capacitance, right? Because we know what is the C in the accumulation. So if I can draw, I'll put it here in the last part. This is my part. Oh well, if I call this A, B, C, D, E, this is part A, this is part B. So part C, I'll do it here. So I know that C ox is equal to C accumulation. That is equal to 100 picofarads. Okay. But remember, whenever we calculate C ox, we have been using C ox is epsilon oxide divided by thickness of oxide. But these units always are farad per centimeter square. That's what we've been using. We really didn't take the area into account. But now we are given the capacitance in farads, picofarads. So then we have to calculate that, right? So then I'll just simply calculate. So we are asked the thickness, right? So thickness of the oxide. Okay, that's straightforward. You just have to rearrange this. So thickness of the oxide is going to be epsilon oxide. Okay. What is epsilon of oxide? So there is one part which is the dielectric permittivity, 3.9, right? The relative permittivity of oxide is 3.9 into the relative permittivity of free space, which is 10 power minus 14, 8.85 10 power minus 14, divided by capacitance of oxide, which is 100 picofarads. Okay. But this is per unit area, right? We have to multiply it by area. Okay, we have to multiply the numerator by area, right? Because area should be here. Let's see, into 3 into 10 power minus 3. Right? Area has to be multiplied, otherwise it won't work. Good. So this will turn out to be, I know the numerator very well. This is 34.5 into 10 power minus 14. I'll divide by 100 by 3. That I know. It's going to be 33.3. And 10 power minus 3 will go. So this will be 10 power minus 9. Okay. So this is approximately 1 into 10 power minus 5 centimeters. Okay. That's what I think it should be. Okay. Okay. So if I take out one more 10 minus, 10 power minus 1, if I divide by 10, so essentially I'll get 0.1 micrometer. Okay. The answer is 10.1 micrometer. Okay, that's how you solve the thickness of the oxide. Okay. And the last question is, assuming delta depletion, what is the minimum? What is the maximum depletion width and the associated doping concentration? So how will we find the depletion width, right? Maximum depletion width, I can call it W max. So always, we are, sometimes we are very, very familiar now, Well, so you can write 2 epsilon silicon divided by Q times Na into phi S, right? And I know the phi S is basically 2 phi F now. Okay. That's it. I can calculate what is maximum depletion width, right? So what is my phi F? Okay, this is very good. So this is your initial tendency. Will this work? Unfortunately, it doesn't, right? Because we don't know. No, we don't know phi F. The concentration is not known to us. We're actually asked to find the concentration. So this approach won't work. So what do? How do we calculate the maximum depletion width? Well, remember, this capacitance, right? Whatever we call it, C min. Right? If I call this as C min, C min is equal to. Let me write it in a different way. Instead of writing it C min directly, I write it in 1 over C min is equal to 1 over C ox plus 1 over C depletion. Right? We know this expression. It's a parallel series capacitor, so we can write it in this like a parallel sum, right? So we know what is C min. This is equal to 20 picofarads. We know what is Cox, which is 100 picofarads, right? So we can find out what is C depletion. Once we know C depletion, we know that C depletion is equal to epsilon silicon by W depletion. We know this. We can use that and find thickness, depletion width, right? When is the maximum depletion width? When it is in inversion. So of course that is going to be valid in this case, right? Because C min is when you have the maximum inversion width. Okay, how do we solve for C depletion now? Well, I can do some jugglery algebra, which I usually don't like, but let me try here. 1 over C depletion equal to 1 over C min minus 1 over C ox. So this will be equal to C ox minus C min divided by C min C ox. What is this? C ox is 100, C min is 20. So this will be 80 divided by 100 into 20. So this will go, this will be 4. And this is equal to 1 over C depletion. So I'll actually write C depletion as 25 picofarads. Okay. That's how it is. So now what is my W max? W max from here will be this equal to W max, right? Because we are in inversion. So I need to write epsilon silicon. So 11.7. It should be 11.7 or 11.8 into 8.85 into 10 power minus 14 divided by, well, I actually need to multiply it by area, I think. Yes, 3 into 10 power minus 3 divided by C depletion, which is 25 picofarads. Okay. So you will find out, right? Some number, you'll get some number. I don't know. You can calculate this. I will leave it to you. How much is it? But make sure that this number should not be, something like 10 microns. Okay. We would expect it to be like 0.2 to 1 micron, something like that, in that range. Okay. It won't be very, very high. If your doping is even 10 power 19, it might become even 50 nanometers. But typically 10 power 15, 16 doping, I think it will be close to 0.8, 0.9 micrometers. Okay. So please do the exact calculations. Okay. So once you know that, you can calculate the doping. Well, how do you calculate the doping then? You know depletion width, so you calculate the surface potential, and then from that you get the phi f, right? Surface potential phi s is going to be what? We didn't use this expression. We have always been using the square root term, but it essentially is half QNA by epsilon silicon times W square. So you put in the depletion width, get the phi s, and that will be equal to 2 phi f. So you will get the answer. Once you get phi f, you calculate KT by Q, ln of, no, not ln. It should be KT by Q, no, not KT by Q, sorry. It should be KT by Q. So you want Na, right? Not phi f. So your Na, or rather Na equal to P in this case, equal to Ni exponential phi f by 0.0256. Okay. Some number, 10 power 15, 16, something you'll get it. 10 power 16, let's say, per centimeter cube. So please make sure that you work out this algebra. We are almost there. You should be able to solve this fully. Okay. So that's the first problem I wanted to solve. And I quickly want to solve the second problem. Okay. So this problem is find the maximum depletion width. And, okay, let's call this as minimum capacitance and threshold voltage for an ideal MOS capacitor with some 10 nanometer gate oxide and p-type silicon, and Na is given to us, which is good. And then include the effects of flat band voltage, assuming N plus polysilicon and fixed oxide charge. Oh, well, this is going to be interesting. Again, it's going to be another long problem. So first thing first, how do we calculate the maximum depletion width? If you want to know maximum depletion width, you need to know the maximum surface potential, or rather, what is the surface potential, right? So that will be 2 phi f. So what is phi f? Okay, that's straightforward. We have done it now hundreds of times. Phi f is going to be, without any steps, I'll write it. This will be approximately 60 millivolts into 6. So that will be approximately equal to 0.6. Is it? Sorry, 0.36 volts. Okay. So please do the exact calculations yourself. Okay. So once I know phi f, I know my maximum depletion width. So this problem is nice in a way that, in the sequence, you just follow the sequence of parameters they are asking and you will get them. Okay. So W max should be equal to 2 times epsilon silicon divided by QNA times 2 times phi f. Okay. You'll solve it. It will be something in the range of point some number, x microns. Okay, micrometers. You find out what number it is. Okay. Please calculate yourself. But when you're calculating, remember, so you should never forget this thing. This is 11.8 into 8.85 into 10 power minus 14. Okay, don't remember that. We always use, don't forget it. Okay, it's farad per centimeter square. So this is going to be important, and rest of it will flow. Okay. So what is the minimum capacitance? Well, to calculate the minimum capacitance, we need basically C min is going to be C ox, C depletion divided by C ox plus C depletion, right? So this is going to be, I need C ox. How will I get C ox? C ox is simply going to be epsilon oxide divided by T oxide, that is 3.9 into 10 power, into 8.85 into 10 power minus 14 divided by thickness of 10 nanometers is going to be 10 power minus 9, minus 7 again. See, this is minus 7. We need to write it in centimeters, not in nanometers. Okay, since we write it in centimeters, we put 10 power minus 7. If you calculate this, the first term will be 34.5, 10 power minus 7. So this will be into 10 power minus 7 farad per centimeter square. Oh, well, there's a 10. So this should be 10 power 8 minus 8. Okay. So it will be 345 nanometer. Okay. This is going to be 345 nanofarad per centimeter square. Okay. Good. So once you know this, of course, you know C depletion. Plug and chug again. I'm trying to put everything in this C depletion equal to epsilon silicon divided by width of depletion. Okay. So you calculate how much this is going to be. I'll leave it to you. Once you calculate C min. This is going to be 11.8 into 10 power, into 8.85 into 10 power minus 14 divided by something that's going to come, W max. Okay. That's farad per centimeter, so it will come out. Yeah. Okay, good. So the other parameter that they want us to calculate is what is VT. What is VT for an ideal MOS device? VT is equal to minus QD by Cox plus 2 times 5. What is QD? QD, this is going to be, it's going to be Na minus, right? The depletion charge is Na, negative charge, so minus will cancel out. So what you'll end up getting is, what is the doping density? Well, you can't directly put the doping density. Another critical thing, remember, the charge, so you have to put 10 power minus 19 into doping density, which is 10 power 16, into the width, which is, I don't know, W max, divided by Cox is 345 nanofarads per centimeter square. So into 10 power minus 9. That is per centimeter square. Okay. So you will get this part plus 2 phi f 2 into 0.36 volts. Okay. You will calculate it. I mean, it will be some number. I guess in this case, it's a ideal MOS capacitor, right? So the VT 10 nanometers might come to be about 0.6, 0.7 something. Okay. VT will be approximately, I don't know, 0.7 volts. You check it out, what exactly it is going to come out to be. I'm not certain. Oh, no. It will be higher. It will be higher because This itself is 0.7. So I would say maybe it's even, if I take this as one, okay, let's try to guess estimate, right? So this I'll take it as I'll take it as 1 micron, just as an approximation. 1 micron. Okay, that's all I need, right? Well, so this is going to be, this will go out. So this will become 10. That will become -6. So that's micron. What are we missing? Anything we are missing here? So 1.6. So this will be, let's try. This will be 1.602 into 10 power -10. Right, -10. Okay, that will be +6 now. This will be 6 into 1 micron. 1 into 10 power -6. No, we can't put 1 micron as 10 power -6. We have to put it as 10 power -4. Okay, because it's centimeters. Okay, divided by 345. Okay, so this will be, if I take this as, this will be 2 orders, right? So I'll take it as 160. 160 divided by 345, 1/2. Okay, check it out, how much this is going to be. Approximately 0.5. Something like that. I don't know what exactly is W max. W max may not be 1 micron. If it is smaller, then if it's 3 times smaller, it will be 0.2. Okay, 0.2, something like that. So I would expect VT ideal to be in the range. If its upper bound seems to be 1 micron. So on the upper bound, I'll have 0.7 plus 0.5, so 1.2 volts. That's my approximate upper bound. The lower bound, I'll take this to be, instead of 1 micron, I'll take it to be 0.2 micron, 5 times smaller. If I take to be 5 times smaller, I'll get 0.7 to 0.82. Okay, so in this range, 0.82 to 1.2 volts. Okay, on an average, you can say 1 volt approximately. That will be the answer you should get. Okay, so why I did this is basically, you need to be familiar with guessing the numbers. You can't, sometimes it requires that you guess and still have the right order of magnitudes. Okay, okay, so this is my VT. So I mean, in a way, this is a sort of laziness, right? To refusing to calculate. But it turns out that when you force yourself, to not calculate, if you have a calculator, you immediately run for it and then you churn out some numbers, but you won't be thinking that much. When you are refusing to calculate, then your mind is forced to think, and then many times you come up with so many interesting solutions. Okay, so it's a good thing that you can do, but of course not in the exams. Exams you need to be exact. Okay, this is only for learning purposes. All right. Okay, so the last part of the question was basically calculate the flat band voltage, assuming N plus polysilicon gate and fixed oxide charge. Well, I have done this in just a couple of videos back, but anyway, quickly let me recap. So what is VT then? VT is going to be phi ms minus interface charge divided by Cox plus VT ideal. Okay, what is going to be phi ms? Well, now it's going to be N plus polysilicon and substrate is 10 power 16. So I'll make my EF to be almost at EC because it's N plus polysilicon, right? N plus poly. This is P type. So I'll take my EF to be somewhere in the middle. Not middle, lower than middle. Yeah? This is my EI. And this is going to be my phi F. So what is phi ms now? Phi ms is going to be minus because phi m is smaller than phi s. Phi ms is negative. Eg by 2, which is 0.56 volts, plus phi f. Phi f in this case was 0.36 volts. So minus 92, 0.92 volts. Okay, this is going to be my phi ms. All right. What is going to be my correction due to the fixed oxide charge? Well, Qi by Cox, right? My Qi is 5 into 10 power 10. Okay. Many times we make a mistake of leaving it at this, and it will give you absolutely crazy answer. This has to be multiplied by the charge, 1602 into 10 power minus 19 divided by Cox is 345 into 10 power minus 9, right? Oh, this is fantastic. I think it is fantastic because this is cancelling out. All this is cancelling out. So what you have is, I'll take 5 into 1.5, that will make it 7.5 divided by 345. Very, very small number, right? I don't know, 1 by 50, something like that. Okay. So it's a small number. So this is going to be negligible. Okay. So what is going to be my VT? VT is going to be minus 0.92 plus, we said it's 1 volt or something like that, right? So this is going to be simply 0.08 volts, something like that, okay, in that range. So you see, this is one advantage of actually choosing N plus poly with P-type substrate. Since you have this large 5ms, which is negative for, if you choose N plus poly P silicon combination or P plus poly N silicon combination, 5ms is going to be large negative, approximately minus 1 volt. You can take it. Here 5ms is going to be not 1 volt, 0.8 to 1 volt or 0.6 to 1 volt, I'll say. Here it's going to be plus 0.6 to 1 volt. Okay. Because in this case of P plus poly N-type silicon, it's going to be 5ms is going to be larger, so it's going to be positive number. So what happens is, when you calculate the VT, right, you had this VT ideal term, which is QD by Cox plus 2πf. That is going to be a large positive number for NMOS devices. So 5ms is going to bring it down. So overall VT of the device is going to be small if you use N plus poly and P-type, and similarly P plus poly and N-type. Okay. Absolute magnitude of VT is going to be small, and it's going to be quite symmetric. This is very, very useful in the newer generations where you don't want VT to be large. We want to accurately control it. So in those scenarios, it's very useful to use this. Okay. All right. So this is what I wanted to cover. So I took some time, but I hope you got a hang of how to solve these problems. There will be a couple of more that we will post as part of the assignments. Please make sure you take your time and solve it. Even though it's going to be simple fill in the blanks, it's going to take you some time to solve it. So we will try to, please make sure that you get the right answers. All right. Thank you so much. I'll see you in the next lecture.